Okay, so last class we took a test. The class before that, we talked about orthogonal projections of a vector onto another vector or onto a line, right? So today we're going to expand our definition of orthogonal projection from, instead of just projecting onto a line, which is a one-dimensional subspace, we're going to project onto more dimensions. Okay, so you project a vector into a subspace that has dimension greater than 1. So here's a picture of it. The orthogonal decomposition theorem basically says if you have some subspace W, which I've drawn as a plane, so we can picture it in R3, and once we leave R3, you can't really picture it, but so I've drawn W as a plane here. It says for any y in Rn, so here's my vector y, going from the origin in the direction of y, right? It can be uniquely written in the form y equals y hat plus z, where y hat is in W and z is in W perp, right? So you can take two vectors, one in W, so the orthogonal projection in the direction of W is this guy down here, right? So you basically have a perpendicular. We drop a perpendicular from y to the subspace W. And then z is orthogonal to W. So you can see y is the sum of y hat and z because the way you add vectors is the head to tail method, right? It's the diagonal of the parallelogram formed by y hat and z. So it's the sum. Yep, no, they're the same vector, just drawn in different spots. Yeah, you could also call this z. It's just that we typically draw vectors starting from the origin. Oh, yeah, yeah. No, y is above the plane. So we've got a plane W, and then we've got y above there. The orthogonal projection of y onto W is where you just drop a perpendicular down to W. Call that thing y hat.
So y hat has y components.
Yeah. Yep. So the way we calculate the y hat and the z is really similar to how we calculated y hat and z when we were projecting onto a line. Okay? It just has more terms. So if you have an orthogonal basis of W, so this only works if you have an orthogonal basis, which in all of your homework problems and activities, I will give you an orthogonal basis, but know that it only applies when the basis is orthogonal. If you have an orthogonal basis of W, y hat is just y dotted with u1 over u1 dotted with u1 times u1, where when this was a line, a basis for a line is just a single vector u, so it only had one term, right? The single vector that was whose span is the line. But now we have p vectors, so you add up all these components. So this picture, you should take some time with this picture because it really explains why this is the formula. So what we learned last class is that you could project a vector y onto a line L. So let's say we have y here. So I can project y onto u1, right? We already knew how to do that from last class. I could project y onto this line, right? And by dropping a perpendicular to the line, and I get y hat. We'll call it y1 hat. You could also project y onto another line, and call it u2. So here's my second line. I project y onto that one by dropping a perpendicular, and you get y2 hat. So y hat, which is the projection onto the entire plane spanned by u1 and u2, is the sum of y1 hat and y2 hat. Right? It's the diagonal of the parallelogram formed by y1 hat and y2 hat. So this is y hat, and that's why you calculate it that way. It's the projection onto the line u1 plus the projection onto the line u2. So that's why it has to be, that's why u1 and u2 have to be orthogonal for the formula to work. because they're already perpendicular to each other. And then y is perpendicular to both of them. So when you add them, you get something perpendicular to the whole plane. Yeah. Yeah, it's hard to draw in 3 dimensions so you can see the perpendicularity. This, yeah, that's perpendicular. That's perpendicular. These two are perpendicular to each other. Okay.
There's a 90-degree angle. Yes.
Yeah. Okay. Okay, so yeah, definitely like this picture sort of explains everything. If you spend some time really thinking about this picture, it should help pull everything together. All right, then we have the best approximation theorem. We'll let W be a subspace of Rn, so picture a plane in R3 maybe. And Y can be any vector in Rn. Y hat will be the orthogonal projection of Y onto W. Then Y hat is the closest point in W to Y. So go back to this picture. Maybe the simpler picture is better here. So here I've got a subspace W. I've got a vector Y that's in Rn. It's not in W. So Y hat is the closest point of all the points in W. Y hat is the closest you can get to Y. Any other point, the length would be longer. Okay. So it's called the best approximation. Y hat is the best approximation of Y. If you had to choose something from W, the closest thing to Y is Y hat. So this is just says the length from Y to Y hat is always smaller than the length from Y to V for any other V in the space. And then quick note on notation, Y hat is also sometimes notated as the projection of Y onto W, proj sub W Y. Okay, and then basically, if Y hat is the closest you can get to Y by being in W, if Y were already in W, what would Y hat be? Y itself, right? If Y were already in W, right, then Y hat would be Y. The closest you could get to Y would be Y itself. And one more theorem. U1 to UP is an orthonormal basis as opposed to just orthogonal. It's orthogonal and all the vectors have length 1. Then the projection of Y onto W is the same formula. It's just the U1 dot U1 is always 1. Right? The denominators go away. So if this is my formula for Y hat, right? U1 dot U1, if those are both unit vectors, would be 1. So the denominators just go away. So you have a slightly simpler formula. This guy. No more denominators because the UI dot UI will always be 1. And then in matrix terms, and I'll encourage you to write this out on your own, but basically if you let U have columns, make a matrix U whose columns are U1, U2 to UP, the orthonormal basis, then the projection of Y onto W is U times U transpose times Y. And it's pretty clear when you write it all out. I'll let you do that on your own. There's a homework problem about that. No, the projection of Y onto W is just another notation for Y hat. So Y hat is equal to U transpose times Y. All right, so I feel like all of that feels really theoretical, and then once we apply it, the calculations are all really straightforward. So here I've got a Y, a U1, and a U2, and we're going to let W be the span of U1 and U2. So verify that U1 and U2 is an orthogonal set, right? Because all of the things we just talked about in the notes only apply if your spanning set is, if your basis is orthogonal, right? If your basis of W is orthogonal. So U1 dotted with U2, is -3 plus 3 plus 0, which is 0, right? So that's how we show that we have an orthogonal set. Yeah. Nope, just dot the u's. If you had u1, u2, and u3, if you had 3 u's, you have to dot each one with all of the other ones. Right, but since we only have 2 vectors, we just dot them, and we show that it's orthogonal. All right, so I want to find the orthogonal projection of y onto w. So y hat is u1. Does it start with y or u1? I don't remember. It starts with y. Okay. Y dotted with u1 over u1 dot u1 times y times u1, sorry, plus y dotted with u2 over u2 dot u2 times u2. So we're basically doing the orthogonal projection of y onto u1 and the orthogonal projection of y onto u2, and we add them together to get the orthogonal projection of y onto the plane spanned by u1 and u2. All right, so y is 2, 2, 3, 1, 3, 0. So you might notice that you had a problem like this on your exam 3 practice that you probably had no idea how to do because it was from 6-3. So that was my mistake, sorry. And then u2 is -3, 1, 2. Okay, so when I dot these, I get 2 plus 6, which is 8, over 1 plus 9 is 10, times 130, plus 2/14 times -3, 1, 2. So I have 8/10. Let's reduce these. This is 1/7. And 8/10 is 4/5. Oh, what a pain. Okay. 4/5 minus 3/7, 12/5 plus 1/7, and 0 plus 1/7, 2/7. Anybody do this already?
I got the last one.
Good job, Topher. Yeah. Oh, great. Thank you. Okay, so there is my orthogonal projection of y onto w. And you calculate z the same way we calculated z in 6.2. It's y minus y hat. So the original y minus y hat, I asked you to do that in one of the activities, so just to remind you. This y hat, I don't think it's a unit vector. Oh no, y hat doesn't necessarily come out to be a unit vector. It will necessarily come out to be orthogonal to z. Whatever you get for z, if you dot product y hat and z, that's just a good check. You should make sure that y hat and z add to y, right? So let's write down good things to check. Y should equal y hat plus z, right? Because that's what you were asked to find. Write y as the sum of y hat and z. And y hat and z are supposed to be orthogonal to each other. So if you dot product them, you should get 0. So that's just a way to check your work when you're done. Mm-hmm. Oh no, because then it would be a different vector. Yeah, can't do that. Yes, because then the difference is, would the difference be the same? No, the difference won't be the same. The difference won't be the same. Just do the subtraction. Well, think about integers, right? If I do 10 minus 5, is that the same thing as 20 minus 10? The difference is not the same. Right.